Hey y'all, welcome back. I'm your personal math teacher, Mr. Boyden, and today I'm going to teach you how assignment within studies works. And what we mean when we say assignment within studies is in the last lesson we learned about how we would have different groups, like a treatment group and a control group. We're going to be learning if you're a subject or if there's an animal that's a subject or if you're subjecting a tomato plant to different treatments. How do you decide which tomato plants get which treatment? That's what we're going to learn today. Before we do that, we're going to do a little bit of review from the previous video. So we have 4 examples here, 4 questions that we're going to consider. I want to invite you to pause the video so you have a chance to read them and think for yourself before I offer my thoughts and my discussion. So do that now, please. Okay, so here's what I think. In the first one, study finds that taller drivers get worse gas mileage than shorter drivers. And that generally is true. Explain why confounding may not allow us to claim that being tall causes you to get worse gas mileage. I think one of the problems with a study finding like this is it suggests that maybe tall people drive in a way that causes them to get worse gas mileage. But probably car size is a confounding variable. Oftentimes really big people have to have bigger cars to fit in, and people who are really small have access to driving smaller cars to get better gas mileage. What about B? An experiment shows there's a strong association between caffeine consumption and lung cancer. What is a possible confounding variable in the scenario? Well, a clear one is smoking. And if that doesn't make sense, we might think about it in reverse. So, for example, consider a person who doesn't drink any caffeine at all. Like they just report, I don't have any caffeine at all. Now, there's a variety of reasons for that, but one thing we might think about is people who reject caffeine outright probably reject smoking outright too. So it's not that if you drinking caffeine would cause you to smoke. It's nothing like that. But if you consider people who really don't want to like take in any kind of chemicals, they're also not going to be smoking. So we might include with that something like lifestyle. And then we'd also want to consider that historically at times like coffee and cigarettes often went together for people back when smoking was more popular. And so in our current data around lung cancer, oftentimes it takes a long time for the cancer to show up after someone starts smoking. So that old pairing may still show up in data. What about C? An observational study finds a strong positive association between ice cream consumption and risk of murder, or in the murder rate. Is it reasonable to conclude that eating more ice cream causes more murders? Guys, I hope it's obvious to you that that sounds silly. This turns out to be true, actually. This is true, and it's verifiable in data. And all it is that it's probably the confounding variable is temperature or weather. It turns out that when the weather's really horrible, people who are prone to murder don't tend to go out and murder. They tend to stay warm and stay inside or stay wherever they are. And then people are outside and interacting more when there's better weather. And so when that happens, people who are murder prone are more prone to murdering because they're actually out with other people. And people who are more prone to stopping in and buying ice cream are more likely to buy ice cream because they're out and it's warm, and eating a cold treat would be good. All right, what about D? If we wanted to measure the impact of caffeine on heart rate, we could give our control group Diet Coke and our treatment group genuine Coke, or just Coca-Cola, if you will. What is the source of confounding? Okay, the source of confounding here is the other ingredients in these two. And so what I mean by that is Diet Coke and Coca-Cola don't have the exact same ingredients, just with caffeine missing. For example, only one of them has sugar. And so possibly sugar would have an impact on heart rate, or Diet Coke has an artificial sweetener in it. So unless we know for sure that those have no impact on heart rate at all, then that's a potential confounding variable. We don't know for sure, but as we design a good study, it's something that we would want to be thinking about and we would want to be careful about. The next 3 things we're going to talk about, again, they're review, but they're super, super important. These are basic principles of how we make our study valid, or our experiments valid. The first thing is we need to have random assignment of the treatments, okay? Or the random assignment of treatments to our subjects. So we assign them to different groups. This has to be done randomly so that we reduce bias, or you might consider, like, what if we let the subjects select what group they were in? There's all kinds of biases that could result from that. Also, we want to make sure that our different treatment groups have demographic similarity. between them. Like we don't want all of one type of person in one group and all of a different type of person in another group. We'll do an example of that down in number 3 in a second. Second thing we need control. We need a control group, okay? What we're trying to do here is we're trying to set a baseline to which we will compare our data, okay? So we need a baseline measurement. Sometimes this is a placebo. Sometimes it's a conventional treatment. There's lots of different things it could be, but we always need a control group in a really good study. Okay, and what that means is we're going to keep all the other variables constant. So remember that example with Diet Coke. The sugar content was not constant between the two treatments, and so that was not a well-controlled study. Okay, so what could we do instead to improve that? And when it says D above, that's referring to Coca-Cola versus Diet Coke. So what could we do that would be better? Well, we could use a caffeine pill, for one thing, versus placebo. That would be better, and only one active ingredient. What else could we do? We could do coffee versus decaf coffee. And decaf coffee still has some caffeine in it, so that's actually not an excellent solution, but it would be better than having all the sugar in there and that having the confounding effect. So that's just a couple really quick, easy things we could do that would be different, that would improve that study. Third thing we need is replication. Again, replication just means that more participants and more data is going to make our study better. So I want to consider an example here with you. So let's go back to that same Coca-Cola versus Diet Coke caffeine experiment. Imagine if we only had 6 subjects, 6 people participating in the study, and it just so happens that 2 of them drink a pot of coffee a day. They're heavy coffee drinkers. And so they're going to have a different response to a little bit of caffeine than people who don't drink any caffeine at all. What is the probability that those 2 will end up in the same group? And if they do end up in the same group, that's really going to mess up our study. Well, let's think about it. So we have our 2 groups. We have our, let's call it our diet group and our regular group. So it is possible that both coffee drinkers end up in the first group and none of them end up in the second group. That's one possibility. It's possible that one ends up in each group, or it's possible that they each end up in this, or they could be the switched version of that, or it could be that none of them end up here and 2 of them end up there. So what's the probability that they end up in the same group? And guys, by the way, this is just flip-flopping the people. That's technically a different permutation of this. So what's the probability that they end up in the same group? 2 out of 4. And so we have a 50% chance that this is totally going to screw up our study. This is one of the problems with using a really small sample size. So what if instead we had 60 subjects and 20 of them were frequent coffee drinkers? Now I want you to notice, guys, that this is the same proportion of the subjects that are frequent coffee drinkers, because 2 out of 6, 20 out of 60, both of those simplify to 1/3. So the question is, would that fix the issue? Well, your gut might say no, but actually it doesn't fix it, but it does start to help. Because consider now all the different things that can happen. Let's kind of draw a line in the sand here. So this was our workup here for a sample size of 6. If we have a sample size of 60 with the same proportions of people, what are all the possibilities? We could have 0 of our people in the, and I'm just continuing this chart on, by the way. We could have none of the heavy coffee drinkers in the diet group and all 20 of them here. We could have 1 in 19 or 2 and 18. And so that looks pretty bad. Those are really lopsided. However, if we keep going, down here in the middle, you end up with a section of this that would look like 8 and 12 and 9 and 11, 10 and 10, 11 and 9, 12 and 8. And so you get these sections in here where you have lots and lots of different like permutations of this that end up in a roughly representative sample, or similar demographics in each group, where you have similar numbers of heavy coffee drinkers in each group. And any of those would be okay. So we would say that's okay. Up here, this is bad. That's going to mess up your study in a big way. But these ones down here, those are going to work just fine. Okay, and so does it fix the issue? Not really, but it does help. It starts to help. And I hope that you can see that if we then made this number like 6,000 and 2,000, that there's so many different ways to have the heavy coffee drinkers split up approximately evenly that actually basically does solve the problem. We're going to see later in the class today, or later in the video today, how we can fix that with other ways, but replication does start to help. So these three key concepts, they work in concert with one another. We need all three of them to have a good study. No single one of them totally fixes a study. Because, for example, even with randomization, over here, you still get really weird stuff if you don't have replication. Okay, so we actually need all of them in order to have an excellent study. Let's look at a specific real-world example now. Okay, again, I want to invite you to pause the video so you have a chance to read this and think about and respond to these questions. Then I'll offer my thoughts. In a school with 500 geometry students, the students are randomly assigned to take the course, either via online lecture or with an in-person lecture. In either group, the lesson lasts exactly 45 minutes, and the same teacher is used with the same lessons. At the end of the year, we're going to compare the scores on the final exam. So, there was no research question given here, and that's what question A is getting at. What is this experiment trying to determine? What is it that we want to learn about? Well, really what we want to know is what instruction method produces better final exam scores. Okay, because they talked about instruction methods. They had online lecture and they had in-person. That's what we're comparing. And then our response variable that we're going to measure the final exam. So it actually is, a lot of times people say like, oh, we're seeing which one works better. Specifically, we're seeing which one works better for final exam performance, according to this. It might be a proxy for overall performance, but in general, we're really only measuring their final exam. What is the purpose of randomly assigning students to the treatments? If you had trouble thinking about this one, or if you had trouble answering this one, think about what would happen if you didn't assign them randomly. Imagine instead that you allowed the students to choose. Which students are going to choose the online lecture, and which students are going to choose the in-person lecture? The in-person lecture is probably going to be students who really value socializing. They're going to probably be students who are extroverts more often than not. Meanwhile, the online lecture, most of your introverts are going to choose the online lecture. Another thing that some people might think is that with the online lecture, that might be students who either are really, really serious and find regular school to have a lot of busy work, or it might be students who simply don't like waking up and getting dressed and going to school, and they don't want to have to do their hair every day or something like that. Either way, if you let the students choose, you're not going to get relatively equal demographics or equal representation in both groups. You're going to have totally different social skills and academic skills in the different groups, and so you don't have control. Okay, when you do that, you've not controlled for the other variables. What about C? What variables were controlled? There were 3 of them. Okay, the first one is, in both groups, the lesson is exactly 45 minutes, so the duration is controlled. It's the same teacher. That's super important. Imagine that if they let the better teacher do online learning, for example, then that would not be a good experiment. And they have to have the same lessons. You can't give them different lessons and then measure the same way. That's not going to be fair to one of the groups, and it's not going to give us accurate data. How did it use replication? It used replication by using 500 students. Okay, 500 students is a lot of geometry students if we're talking about one school, so that's where the replication comes in. It would have been much easier to use 5 students, but then you could get some really weird features in your data that would not be accurate. Now we're going to look at 3 different common methods of how we assign treatments to the participants, or we assign participants to treatment groups. Okay, and I'm just going to read them out really quickly so you know what they are. The first one is a completely random design, so let's bold that. The next one is a randomized block design. And the final one is what's called a matched pairs design. Okay, and I'm going to provide visuals for each of them. I think the visuals are pretty helpful. If you want to draw the visuals, please give yourself a chance to pause the video. You might want to pause the video and just read it anyway first. So here's completely random design. Guys, it's exactly what it sounds like, and it's analogous. When we learned about sampling, it's analogous to a simple random sample, very similar. It's just that we're randomly assigning the subjects to the treatment groups. So in this one, group 1 had 30 students and group 2 had 30 students. So what that means is our total number of participants is 60. So the way we would probably do that is we would do a random number generator, or a random integer. We would select 30 numbers from 1 to 60. And those 30 numbers, maybe we would put those 30 numbers in group 1. And then the remaining that were not selected would go into group 2. And so then in this one, what they're doing is they are giving no practice exam to, that's treatment A, they don't get to have a practice exam. In treatment B, they do get to have a practice exam, and then we're going to compare the results. Now the way we would compare the results, typically what we would do is we would find the mean, or the average for each of these. And we would find the standard deviation. We'd use what's called a confidence interval, which we'll learn later. And or we'd use a significance test, which we'll learn about later as well. And then we would compare those two against one another. Okay, that's completely randomized design. One thing that I would like you to know is it is possible to have more than 3 groups. In fact, we could have lots and lots and lots of groups. We did an example last week where we had tomato plants, and we had that they were going to get different levels of fertilizer and different levels of water. And so what we had is we actually had 8 different groups that we were going to use. We didn't use a control group because the control group would have meant no water at all. Kind of no fertilizer is kind of a control group actually. But someone said, no water. No, we're not going to skip watering the plants. That's too predictable what's going to happen. So we had 8 different groups. So you would imagine that a diagram then would split out in 8 different ways. Now it looks like a lot, but that should be an easy way to actually help us keep track of which treatment is which and which group is which. Still, we would just compare the means at the end with the data. So that is completely random design. Just do be aware that it's not limited to 2 different groups. All right, next is randomized block design. This is a little bit more sophisticated, and it's considered to be a little bit better. Okay, so what we do in this case is we sort our subjects into blocks. Blocks are just groups. Now, it's not stratified sampling, okay, but it's very similar. Okay, it's like putting them into strata. Remember, strata for sampling were groups that we thought would have like characteristics which might impact the results that they give. Okay, so we're going to look at some examples down here in a second. So within each block, each subject is similar in some way that is thought to impact their response to the treatments. Now we have an example diagram below here. In this one, they have 10 volunteers. Oh, that's not very good replication. That's not good. But what they did well in this one, and what are we trying to figure out? So we are measuring typing speeds. So what we want to know is something about typing speeds. What are the treatments here? The treatments are 2 different keyboards. And so treatment A is keyboard A and treatment B is keyboard B. I also want you to notice that keyboard A appears twice. What the heck? And so does keyboard B. Why is that? Because what we've done is we looked at these participants and we noticed that some use smartphones and some don't. And we think to ourselves, wait a minute, if someone doesn't use a smartphone, they're probably going to have a very different performance on a typing test than somebody who, or at least on average, we should say, than the average smartphone user. Especially this looks like it might be a phone keyboard, potentially, or different keyboard layouts on a phone. Okay, so what we do is we block like this, and then what we do by random assignment, we make sure that 2 of these 4 people get keyboard A, and 2 of these people get keyboard B. So we've split them up. Okay, and that would be a solution to that Diet Coke versus Coca-Cola experiment from earlier, which we'll talk about that in a second. So, and then we could do the same thing with non-smartphone users. They get randomly assigned with a random number generator, probably split up. And then at the end, we combine the results. Now, that's not explained in this diagram, but I want to show you what that would look like. What we would get is the average for keyboard A. And then we would also get the average for keyboard B. And we would compare those. So we're going to be aggregating our data here at the end. All it is we're just practicing different assignments. So like all the data that come from what I'm highlighting here in green, we're going to put those together into one data set, because what we're trying to answer is which keyboard is faster, keyboard A or keyboard B. And that's how we're going to be able to tell. Let's draw a diagram for that experiment that we talked about earlier with Diet Coke. Was it Diet Coke? Let's go back and look real quick. So I had said, yeah, let's do this one right here. So what if instead we had 60 subjects and 20 of those were frequent coffee drinkers? Okay, so 60 subjects. So we're going to start out with 60 subjects. So I'm going to say 60 humans. And let's do some blocking. Blocking would look like this. So coffee drinkers and non-coffee drinkers. They said there were 20 coffee drinkers, and that implies that there would be 40 who are not heavily drinking coffee. Okay, and so let's randomize. And let's randomize. And in this example, what were we randomizing them to? Yep, caffeine experiment. Now let's use the better version of the caffeine. Let's use the caffeine pill versus placebo. Okay, so we're going to randomize these people so that 10 of them get the real pill. So I'm going to put let's put caffeine here. And let's do placebo, caffeine. Notice each of these appear twice. Placebo. And each, so then these 20 people got split up. So we're going to make sure that 10 of these get caffeine, 10 of them get the placebo. Down here, there's 40 people, split them up evenly. So 20 get caffeine and 20 get placebo. And then what we're going to do is we're going to combine the results back together. And so in effect, actually, I'm going to draw this a little differently than the previous diagram. So in effect, or I should say, you know what, we have to measure heart rate. So measure change in heart rate. And then we're going to combine and analyze data. Oops, that doesn't look like analyze though. Haha. Combine and analyze. Okay, so there's another diagram of randomized block design. Okay, now it does need to be randomized blocks. You can't just choose the assignment to the groups. Like I can't just say like, oh, I'm going to pick my favorite people and give them the caffeine because they'll like it. No, we have to randomize. Okay, it is possible to have more than 2 blocks. Like for example, we could have done a blocking scheme here. They're called schemes. We could have done a blocking scheme where we had one group where the people drank 1 or more pots of coffee per day. We could have people that drink 0 to 1 pots per day, and we could do no consumption. And so it's up to us how much we want to block it. What we're going to do, though, is we're going to block it in a way that makes it as easy as possible to get the most valid result possible. And so if we believe that having more blocks will be more representative and make sure we get equal representation into the caffeine and placebo group, then that's what we would do. So guys, that is what randomized block design is. Okay, let's look at another one. This is another method. Now this is called a matched pairs design. And this is sort of the gold standard of experimentation. If we get an opportunity to do matched pairs design, then that's what we want to do. You know, and in fact, a lot of the studies that we've talked about already today, they sort of are a matched pairs design in disguise. So I'm going to try to play that out here. Okay, what a matched pairs design does is it compares 2 individuals who are thought to be similar for purposes of the question that you're trying to answer. An easy way to think about this would be any sort of twin study, where you have 2 identical twins and you subject one twin to something, you subject another twin to something different, and you see how they respond differently. Especially with things that are physiological, they have the exact same genetics. And so you would then say, oh, okay, well, if this treatment causes this effect, or if this treatment causes that effect, then it's on the same genetics. And that means there's lots of control in that experiment. Now, one of the things that's not as explicit in AP is that those 2 individuals, they can be the same person. Let me give you an example. An example would be if you wanted to test a cholesterol medication. In that case, person one would be any, and I'll just say you just for ease of thinking. So it would be you before taking the new med, or your, I should say your cholesterol. So let's do LDL cholesterol, for example, your LDL before taking, and then you would come back and you would get a a blood test in 6 months or something, and it would we would pair the first data point with your LDL after taking. Okay, and so here's the key that makes it match pairs. Let's say, and I'm gonna totally fudge this. If any of you know about LDL cholesterol, please be nice in the comments. I don't know what real numbers would be, but I'm just gonna make up numbers here just for the sake of illustration. Let's say your number was 50 before, and then it was 40. So what we're going to do is we're going to combine those together in one number, and that number is going to be -10, which signifies a 10-point drop in your LDL cholesterol. Okay, so that's going to be a single data point. So then when you hear a study that says, like, on average, people lost 10 pounds or more with Bilenix or whatever the drug is, that's what it's based on, this match pairs idea that you're going to have a data point from each person before and a data point from each person after, and then that's going to be able to show you how much they dropped. It's supposed to show you how much weight they dropped or how much cholesterol they dropped as a result of that. Okay, so let's go back and look at the diagram on this for just a second. So they have over here, they're going to have a pair. In that pair, they're going to randomly assign one to one treatment and one to another. Okay, now that doesn't necessarily hold up here, even though that technically is match pairs, but we can do that. Another way of doing this, let's say I wanted to test an ointment that's supposed to reduce soreness in your hands after playing video games. The first pair, it could be my left and right hands. Okay, so like I own both of the matched pairs. I have both of them, and so maybe I get the active ingredient in treatment 1, and I get the placebo on 2, and they look the same. So it's a blinded study, and it's randomized which hand gets the active and the placebo, and they ran lots of video gamers through that same treatment. That's a totally valid way of running a study, and then I'd report back, well, my left hand feels this way and my right hand feels this way. Okay, and then we compare my scores or my pain scores on either one of them. Okay, that would be a totally valid way of doing this. So I guess my point with all this is, a lot of times we think of match pairs as there has to be 2 individual human beings or 2 individual plants or whatever. Not necessarily. We could do the same thing with different branches on a tree or different leaves on a plant. Okay, you could have one sort of life form that is its own matched pair, especially if it has 2 of something. Let's do an example to end our video today. So let's say that there's a drug company and they're going to do a trial, and they want to compare a new drug against a conventional treatment for reducing cholesterol level. And below we have a table that summarizes the subjects in the study. Okay, so let's take a minute to understand the table. We took down more information than just the cholesterol level on each person. We took down their sex, we took down their cholesterol level, we know their age, and we know their weight. This would be a common thing that we would do. And let's see what we're asked now. Describe how we could use completely random design for the study. Y'all, as we go, in fact, let me put all the questions on the screen, and I just want to give you a chance, if you want to pause the video and think through these for yourself before I spoil them for you. Spoiler alert, we're going to have the answers here in just a second. All right, how could we use completely random design? Completely random design is kind of mindless. We would just select 10 numbers at random, and so we use let me say use a random number generator. Use random number generator to select 10 numbers from 1 to 20. Those selected are in the new treatment group, and the rest would obviously be in the other group. It's super simple, it's super easy. As we saw earlier, though, it has the potential for some sort of demographic problems. How could we use randomized block design? Okay, so what we have to first decide is, what feature do we want to block by? We have options here. We can block them by their sex, we could block them by cholesterol level, we could block them by age, or block them by weight. Now, y'all, I don't claim to be a doctor. I'm not anything medical. Actually, I'm a math teacher. But what we know though is if we had some sort of knowledge about factors which impact cholesterol level, then we'd probably want to use that. So let's say, for example, that men and women react very differently to some compound in this drug, or that men and women react very differently to cholesterol level in general. If that were the case, then we could block by sex or gender. And when we did that, so then we would have, what would we have? How many males? We'd have 11 males is one block, 9 females is the other block, and then randomized treatment within each block. Now, you may have noticed, wait a minute, not only are there different numbers of males and females in the study, there's not an even number of each. So this method guarantees that you will have a different number of males and females in each treatment. Is that a problem? In this one, maybe. Yeah, we don't have very good replication because there's only 20 participants. So in this one, yeah, that's potentially an issue. It's an issue that's easy to see. There's issues in the same way with using just completely random design, and so it would be really hard to see that one. That one be as obvious. But these both have some issues, each of which would be, if not fully resolved, very greatly aided by having some more replication. How would we do this as a match pairs design? A match pairs design, we'd have to, in this case, we'd probably pair up the individuals. And so what I think the easiest way to do this by, and the most relevant way to do it by, would be to reorder the list by cholesterol level. Oops, I misspelled cholesterol. Cholesterol. And then the 2 participants with the lowest levels are a pair. The next 2 highest after them are a pair, and so on. And then obviously participants. And then we obviously have to randomize which gets which treatment. And that would be if we think that people with a lower cholesterol level are going to react differently to this drug than people with a really high cholesterol level. Okay, and so that would be a little bit better. So in this particular example, what are the best and the worst designs of these? My opinion is the match pairs is the best. And part of that is because I don't know very much about medicine or cholesterol or, biochemistry. Okay, I don't know anything about biochemistry, in fact. So I suspect that match pairs is going to be the best because at least you have people with similar levels being split up into different groups. Blocking is probably the next best because at least then you have some factor that you're trying to control for. In this case, it's sex or gender. And then completely random is probably the weakest because we're not controlling any other variables. Guys, you see that we've listed out 4 variables up here: sex, cholesterol level, age, and weight. Any one of those is potentially a confounding variable. And so both blocking and matched pairs give us an opportunity to try to control some of the confounding. And a doctor would know much better than us about which one of those it's most important to get control of. And so that's how they would decide this, or a medical researcher would know better than us. And so they would figure that out. But for us, what we can know for now is that matched pairs and blocking are better. Completely random is quite a bit weaker. So what did we talk about today? We talked about the key concepts of experimental design. We talked about randomization, control, and replication. We also looked at 3 different methods for designing a study. We looked at completely random design. Let's highlight it. We looked at completely random design. We looked at randomized block design. Notice the random. And then we also did a matched pairs design. And guys, remember, there is still random assignment in a matched pairs design. You don't get to choose just on your, on your own whims which person or which item in the pair gets which treatment. Okay, those are the 3 well-known ways of doing this. It's what AP does, and it works in almost all fields of study. So that's going to be it for today's video. I hope you enjoyed the video, and I'll see you next time.